So now we're going to look at exponential growth and decay. What you've seen before are equations like if you have an initial amount and you have a doubling power over a certain amount of time. You've seen these sort of formulas where you have different bases. Now we're going to look at exponentials with a base of e. So it's a function in terms of t. Your PO is your initial amount, and it's your exponential growth based on a growth constant k. Now, it's considered a growth constant if it's a positive value here. If you have a negative here, where k is a positive value multiplied by the negative, then it's considered a decay. Now, there is a theorem that says that if you have a differentiable function, which they refer to as y of t, and you can actually find its derivative, and you get some constant times the original y of t, then it has to be of this format here. So it has to be a growth formula. An initial amount multiplied by your base of e raised to a constant k with respect times by t. And also, more importantly, is that the initial amount is just when you plug in 0 into your original function. So find all the solutions for that satisfy this, which is exactly this, some constant times your y, where the derivative is equal to 4 times your original function y, where your y of 0 is equal to 5. Okay, so what you need to actually do is consider that if it is a differential function that satisfies this, then we know that y of t has to be of this format, just based on this theorem above. So if that's true, and we find the derivative of this, we know that your constant is going to remain your constant up front. You're going to have your e to the kt, because when you take the derivative of e to anything, it's just going to become e to that value, multiplied by the derivative of the exponent with respect to t, so it's going to be times by k. So your derivative is going to have p to the o times by e to the kt times by k. This is your original function, y of t. So now we have y prime is equal to y of t times by your k. So if we have this fact here, and we know that the derivative is this here, my k is going to have to equal to 4 to make it 4y, 4y. Then we also need to know when y of 0 is equal to 5. So we know our y function is this. We now know what our k value is. So we want y of 0 is going to equal my initial amount, PO, which we don't know yet, multiplied by e to the 4t, and in this case t is 0 that we're plugging in. So y of 0 is going to equal PO and then e to the 4 times 0 is 0, so that becomes 1. E to anything to the power of 0 is 1. So we know that the initial amount is going to be 5. So our function of interest is going to have an initial amount of 5, and we're going to have an exponent of 4 to the t. That's your solution. That satisfies it, so that when I take the derivative, it's going to equal 4 times the constant, where the initial condition is held. Another important concept is when we have doubling time and half-lives. You've seen these sort of concepts before. Now we're going to again work with them with a base of e. Now when we have a doubling time, if we were to look at rearranging the formula, just divide both sides by your initial amount. We know that doubling time is going to be increasing, so we're going to have a positive exponent. Half-lives are going to be decreasing your amount, so we're going to have a negative exponent. That's basically the difference between the starting facts in these two equations. Now, if we're looking for a doubling time, we're interested in when the initial amount gets doubled. So ultimately, this portion right here becomes 2 times your initial amount over your initial amount, which crosses out to give you just 2. Whereas here, a half-life, based on our initial amount, we're going to have half of our initial amount. Again, those cross out and you're left with a half. So ultimately what we're looking at to find doubling time, to isolate for t, is to solve for t in both of these cases. When will it equal a half for a half-life? When will it equal 2 for doubling time? So the only way to solve for your exponent is if you log both sides. Now, we are working with a base of e, so we're going to use ln. And we know that if we take ln of e to the kt, we can bring our exponent out front. And ln of e just becomes 1, so we're left with just kt. Same thing here, we'll have ln of a half is equal to negative kt. If we isolate for t, we divide by k on both sides, so t by itself is going to be ln of 2 over k, whatever our constant was for this doubling equation, and this is considered our doubling time. Now in this case here, it's very similar, except for we've got a fraction here, we've got the negative here. Again, we want to isolate for t, so we're going to divide both sides by negative k. But first, I'm going to work with this side here and put this, instead of having a fraction, I'm going to write it as ln to the 2 to the negative 1. The negative exponent can move out front, so now I have negative ln of 2 is equal to negative kt. If I divide both sides by negative k, they cancel out and become a positive. So in this case here, t is going to equal to ln 2 over k. Same thing, that gives you the half-life.